Right, hello and welcome. This is Course 2 in Technology Fundamentals, Session 3 on Inferential Statistics. In this session, we will look at the utility of exploratory data analysis combined with inferential statistics. Importing some modules we've seen before, our workhorse today will be the SciPy module. Also loading in a new data set. This is a make-believe company that sells truffles, that is little chocolate candies. We have the last two columns indicating the quantity ordered for a given truffle type, the margin on that order, and earnings before interest, taxes, depreciation, and amortization over kilograms. So you can think of this as profit margin. We have a date column, a customer column. We are shipping truffles to another distributor who will actually distribute the truffles. And then these categorical columns. Let's look at what those are. All of our descriptors will be everything except the last two columns. So everything but kilograms and EBITDA per kilogram. And I am here just looping through my columns and printing out the column name, printing out the unique levels in that column. First column, base cake. We can think of this as the meat, if you will, of the truffle, the core of it. And we have 6 different types: butter, cheese, chiffon, pound, sponge, and tiramisu. We have an overall truffle type. Some will have a candy outer shell, some will have a chocolate outer shell, and then some will be jelly filled. We have a primary flavor and a secondary flavor, as well as a color group. And then the customer or distributor that we are shipping the order for, as well as a date. Looks like we have every month in 2020. Up until now, we've been talking about descriptive statistics. So returning the mean, the median of a group, doing some kind of very simple aggregate summary of data. Today's a little bit different. We're going to be looking at distributions of data, distributions within our samples to make inferences or generalizations about the populations that those samples were drawn from. Okay, so this is what we're doing today. This isn't going to be an exhaustive notebook on statistics, rather it's just to get us familiar with some of the methods out there so that when we go to do machine learning for our jobs or our projects, we have some tools in the back of our mind to apply to make sense of our data set before we go willy-nilly applying machine learning models. One of the tests that we'll spend a lot of time on today is Moods Median, and that's where we'll start. We'll also spend some time on analysis of variance. It's a very popular machine learning algorithm, or excuse me, a very popular analysis method that you see in machine learning notebooks. We'll talk about very briefly when we use each of these. We, again, don't have time to go in depth. You could spend a whole semester in a graduate course talking about these things. And here the idea is to just apply them to some simple examples so that we are familiar with the ecosystem of tools that are out there. And it will be our own prerogative to dig in deeper into these topics when the need arises. All right? If you want to look at some information on when to use each of these, this resource from Minitab is good and simple. You can follow it at your leisure. What is Moods Median? This is a special case of Pearson's chi-squared test. We create a table that counts the observations above and below a global median for 2 different groups. We then perform a chi-squared test of significance on this contingency table. The null hypothesis of Moods median testing is that the medians are all equal. That is, the samples that we are analyzing are drawn from the same distribution. The chi-squared test statistic is written as the summation of the observed minus the expected frequencies squared over the expected frequencies. Let's take an example. All right, let's pretend we have 2 different shifts of workers, shift 1 and shift 2. I'm going to make up some data around their performance for creating products. Let's pretend the units in this are in kilograms per minute. All right, we're just making this up, kilograms per minute. Shift 1 is going to be drawn from a normal distribution centered around 16 with a standard deviation of 3. and shift 2 will be drawn from a normal distribution with a mean of 24. And we have our two data groups here. The point of this test, and the point of all tests we will talk about in this notebook, is to figure out if the categorical variable that is included with some kind of continuous variable affects that continuous variable. All right, that's it in a sentence. That's what we're going to be doing in this notebook. And in here, this example, we're looking at this production rate, and we're going to look and see if the shift is significant in determining this production rate. And hint, we know the answer because we created these distributions, right? It's pretty nifty. I know that shift 2 is drawn from a 24 average distribution, and I know that shift 1 was drawn from a 16 kilogram per minute average distribution. And we're going to look and see if median testing will allow us to uncover this without knowing the distributions that these were drawn from. I'm going to use SciPy to do this. And within SciPy, the stats module, we have this test called median test. This is the moods median test. I just feed it my shift 1 and my shift 2 data. And it will return the contingency table, the grand median, the p-value, and the test statistic, the chi-squared test statistic. All right, I'm going to run this. I see that Pearson's chi-squared test statistic is 7.2. We'll compute this for ourselves down below. The p-value of the test is 0.007. Quick note on p-values. Whenever we perform a statistical test, we always end up checking the p-value. And if it's below a significance level cutoff, usually 0.05, we conclude that we can reject the null hypothesis. In this case, we would conclude that indeed these two shifts are drawn from different distributions. They're not drawn from the same distribution. The grand median is 19.5. All right, let's talk about this a little bit more. We also returned the contingency table. Let's talk about what that is. If I sort shift 1 myself, this will make a little more sense. Now I'm sorted from lowest to highest, and we see that 8 of the values are below 19.5 and 2 of the values are above. If we look at shift 2 and sort it, we see that 2 of the values are below 19.5 and 8 are above. And this is reflected in our contingency table. Shift 1 has 2 above and 8 below. Shift 2 has 8 above and 2 below. All right, now I'm going to put these into the chi-squared test statistic and evaluate the outcome myself. Okay, so I'm just doing by hand what we had SciPy do for us. Let's talk about each of these values. The observed values should make sense, right? We have the observation of 2 above for shift 1, 8 below for shift 1, 8 above for shift 2, 2 below for shift 2. The expected values, why are the expected values for each one of these groups always 5? Well, let's think about this. If there are 10 samples in each of the shifts, if I am assuming that each shift is equal, that is, they're drawn from the same distribution, within each shift of 10 samples, I would expect 8 to be above the grand median and 5 to be above the grand median and 5 to be below, right? That's the definition of a median. Now, these expected values would be different for shift 1 and shift 2 if I had different samples, if I had different numbers of samples for shift 1 and shift 2. For instance, if I had 20 samples in shift 2, my expected value for above would be 10, and my expected value for below would be 10, right? So this should make pretty good sense. It's just the definition of the median. I'm going to plug these values in, and indeed x squared evaluates to 7.2. Our p-value, or the probability of observing the null hypothesis, is also under 0.05, so we can conclude that these shift performances were drawn under separate distributions. For comparison, let's do this analysis again with shifts of equal performances. All right, so I'm going to talk about shift 3 and shift 4. And I'm going to draw from a distribution centered at 16 and do the whole test over again. We see that the chi-squared test statistic is 0 because our observations above and below are 5, matching the expected values, so that evaluates to 0. And then our p-value is 1, the grand median is 15.5. Again, we can look at the raw shift values. With a grand median of 15.5, we look at our sorted shifts and see that 5 are indeed below and 5 are above for both groups. And we can look at the reported table as well. When to use MOODS? MOODS median test is highly flexible and has the following assumptions. Considers only one categorical factor at a time. In this example, we looked at the shift. The response variable is continuous, and those are our shift rates. The data does not need to be normally distributed. You might sense a hint of this because we're evaluating a median, and a median is robust against outliers and against different shapes of distributions. The distributions must be similarly shaped between the groups. Sample sizes can be unequal and small. As we saw in this case, we had only 10 observations in each group. Other considerations, not as powerful or as conclusive as the Kruskal-Wallis tests, but still useful for small sample sizes or when there are outliers. And now for an exercise. Part A, perform MOODS median test on base cake in truffle data. And while we're doing this, we're also going to get some practice with pandas group by. This was a new topic for us quite recently, and group by can be a little confusing. So let's use this as an opportunity to better understand the group by method in pandas. I'm going to take my data frame and say group by base cake. And I'm going to set this equal to a new object called GP. And I'm curious, what is GP? Well, one way to find out is to just iterate through it. Seems to be a tuple of some sort, right? I'm just going through GP one time and then break out of the loop. I know it's a tuple because I see these parentheses here. And it looks like there's two different objects. So I'm going to print out the first object, which looks like it's the group name, butter. And then the second object appears to be the data frame associated with that group. That kind of makes sense. I grouped by base cake. And as we saw way up above, there were how many base cakes? I think 6. We can double check that here. By doing df.columns. Let's grab that first column, base cake, df, base cake dot unique. Right, butter, cheese, chiffon, pound, sponge, and tiramisu. Okay. So now base cake seems to be grabbing that first example of base cake type butter, creating both a label and a data frame for it. Going back to our diagram from our earlier Panda session when we talked about group by, it looks like whenever we split in the group by method, we create separate data frames as well as their group label. Right, so we're here in the split step, and we've split upon X, which in our case is base cake, and we're looking at the first group, which in our case is butter. All the A's are butter. It creates both the data frame and the label butter. Okay, so we know GP is separate data frames. How do we turn them into arrays to then pass to median test? Because remember, we need to just provide median test with the raw values of the continuous variable that we want to assess. Let's complete this for loop. It's asking me, turn J into an array using the dot values attribute. All right, so I'm just going to do J dot values, and then it says to print this to the screen. So I'm going to take this, start a new line, and do print J.values. Interesting. What do we notice about this? We're getting all the values in the data frame. And that's not what we want, is it? We want to have just the continuous variable, which in our case is EBITDA per kilogram. So we're going to print the EBITDA per kilogram values to the output. Excellent. And now we have those values. After you've completed the previous step, turn this into a list comprehension and pass the result to a variable called margins. All right, so we'll do margins equals your list comprehension here. So we'll do just exactly what we did above, J EBITDA per kilogram dot values for I, comma J in group by GP. Seems to work fine. Remember the list unpacking we did for the tic-tac-toe project? I think I remember that. We talked about that with the visualize tic-tac-toe function. We're going to do the same thing here. Unpack the margins list for median test and run the cell below. So here I think is where I want to unpack margins. So I'll do that here, and I think it was just an asterisk. Cool. The Pearson's chi-square test statistics is 448. The p-value is very low, and the grand median is low as well. Part B. View the distributions of the data using matplotlib and Seaborn. What a fantastical statistical result we found. Can we affirm our result with some visualizations? I hope so. Create a box plot below using pandas. In your call to df.boxplot, the by parameter should be set to base cake, and the column parameter be set to EBITDA per kilogram. Let's try this. So I'm going to do df.boxplot, and by is going to be equal to base cake, and column is going to be equal to EBITDA per kilogram. All right, looks like we did it. And we can see that the IQR regions are indeed quite disparate between the different base cakes. Oh, and look, we have a nice little comparison using the Seaborn library here. That looks pretty nifty to me. Very clean and a nice size. Perform Mood's median on all the other groups. Recall the other descriptors we have. Right, so we did this for base cake, but we have 1, 2, 3, 4, 5, 6 others we can look at. And so we're going to want to loop through and do this for all of our other groups. So I'll go ahead and do that. For desk and descriptors, so this is going to be what we want to isolate our categorical variable on. So let's try the same thing we did above. Above we did or J rather, EBITDA per kilogram dot values for I, comma J in group by, but we don't want to do group by anymore. We have to remake the group by object because we want to group by a different descriptor every time. So I'm going to do df.groupBy desk. That should be okay. And then we want to unpack these margins into median test. So we'll delete this and just do margins. For IJ, we need an in there. And there we go. We have base cake, truffle type, primary flavor, secondary flavor, color group, customer, and date. And it looks like our highest scorer is the primary flavor, followed by the base cake, followed by the secondary flavor, the color group, the truffle type, and then customer and date that look like they don't pass our significant test at all. It's always helpful to have a visualization. So here, part D, we will finally confirm these visually. Complete the box plot for each group. So again, we took what we did in parts A and B, and we're just throwing them into a for loop. So my X variable here will just be desk. All right, so we have our base cakes looking very different from one another. Our truffle types looking a little more similar, but jelly filled looks quite a bit different from candy and chocolate outer. Our primary flavors, our label is hard to see. This might be something we would consider changing down the road, the way these labels are written out. Secondary flavors, some variation as well. Color group. And then customer and date looks pretty flat. And we saw this in our moods median test, right? For customer and date, our chi-square test statistic is both low, and our p-value is pretty high at 0.2 and 0.9. Our p-values do not pass a cutoff of 0.05. Here's a little enrichment topic. We won't spend a lot of time here, but just as a side note, there are both one sample and two sample t-tests. We would use a one sample t-test just to determine if the sample mean is equal to a hypothesized population mean. And then within two sample t-tests, we have independent and dependent t-tests. The independent question depends on whether we believe the samples are uncorrelated or correlated with each other. For independent two-sample t-tests, we would call upon SciPy with scipy.stats.t-test_ind and then set equal variance parameter to true. To do the same with the unequal variance two-sample t-test, we would call upon the same module but set equal variance to false. By the way, this is also called Welch's t-test. For dependent t-tests, so these are samples that we believe are correlated, we have scipy.stats.t-test_rel. A full discussion on t-tests is outside the scope of this session. We can refer to Wikipedia for more information, including formulas on how each statistic is computed. But we just wanted to make note of the modules that are available to us within Python. And we'll skip over this demonstration of t-tests for this notebook, but feel free to walk yourself through it if you are interested. And again, it's the same idea as moods median. We have two different samples, and we want to affirm or disaffirm that they are drawn from the same distribution. And we just use the appropriate t-test for that question. All right, on to analysis of variance. ANOVA uses the F-test to determine whether the variability between groups is larger than the variability within the groups. If that statistic is large enough, you can conclude that the means of the groups are not equal. The caveat is that ANOVA tells us whether there is a difference in means, but it does not tell us where the difference is. For instance, if I am looking at the base cake column in the truffle data, it will tell me if that column is significant or not, but it won't tell me, for instance, whether it's the butter or the chiffon level that is different from the group. To find where the difference is between the groups, we would have to conduct a post hoc test. There are two main types of ANOVA, a one-way or one-factor ANOVA and a two-way or two-factor ANOVA, where factor is an independent variable. And here we have a table to help us talk about this. A one-factor test would look at either columns A or B and their influence on the dependent column, here on the right. A two-factor would look at both columns together. Our ANOVA hypothesis is the following. The null hypothesis is that the group means are equal, and the alternative hypothesis is that at least one group mean is different from the other groups. And again, it doesn't tell us which group that is. ANOVA has much stronger assumptions than moods median, and for that reason we have to be more particular about where we apply it. But when we do apply it, its conclusion is stronger. The assumptions are the residuals, or the experimental error, are normally distributed, and we can test this with Shapiro-Wilkes test, which we'll show in a moment. The homogeneity of variances, that is, the variances are equal between the groups, we can test this with Bartlett's. Observations are sampled independently from each other. And a side note, ANOVA assumptions can be checked using test statistics like we've listed above, but we also have visual approaches such as residual or QQ plots. Steps for ANOVA. Check sample sizes. Equal observations must be in each group. Calculate the sum of square between groups and within groups. calculate the mean square between groups and within groups, which is based off the sum of squares, just normalized by the degrees of freedom, as we're indicating in the table down here. And then calculate the F value, which is a ratio of the mean square between groups and the mean square within groups. Right? So again, we're looking at the difference of variation between the groups versus within the groups. And the idea is that if the variation between the groups is significantly higher than within, then those categories significantly affect the outcome that we see in the samples. These should look somewhat familiar. SSB, the sum of square between groups. We just look at all the data points and subtract them from the total average. Right, so we take the average of each group and subtract it from the total average, square and sum. The sum of square within groups, same idea, but now we are looping through the individual observations in each group and subtracting that from the group average, and then doing this over all groups. The SST, the total sum of squares, is the sum of these two numbers. Let's go back to our shift data to take an example. We had shift 1, 2, 3, and 4. We found that shifts 1 and 2 were very significantly different, whereas C and D were more close to each other. We can, by the way, produce this box plot with Seaborn, and Seaborn has a nice little feature called a swarm plot. All right, we're just appending the swarm plot over the box plot, but see how it puts the actual observed data points over the box. It's kind of neat. This works really well when we don't have that many observations that would otherwise cloud the box plot. Anyway, back to ANOVA. Again, we're not going to derive this ourselves. Rather, we're going to use the stats module, and we're going to have it do our one-way tests on each one of these shifts. We see that the F value is 10.7, right? So that's the ratio of the variance between groups over within groups. And our p-value is below the 0.05 cutoff. We can get this in the format of the table we saw above, right? So I'm just referring to the table that we created and marked down here. So we're looking at the sum of squares between groups, the degrees of freedom. There are 4 groups, so there are 3 degrees of freedom in terms of groups, 40 observations, so 36 degrees of freedom in terms of the total observations, F statistic, and then the p-value. I do not think I ran this cell. There we go. Those are the updated numbers for this randomly seeded notebook. Okay, so that is the results of our ANOVA, but it is always good to check that the assumptions are met. The Shapiro-Wilk test can be used to check the normal distribution of residuals. The null hypothesis is that the data is drawn from a normal distribution. And so in this case, we would like to conclude that the null hypothesis is valid, and indeed it is because our p-value is above 0.05. We can use Bartlett's test to check the homogeneity of variances, that is, the null hypothesis. Samples from populations have equal variances. And again, our p-value here is well above 0.05. So we can say that the null hypothesis is valid. ANOVA interpretation. The p-value from ANOVA analysis is significant, less than 0.05, and we can conclude that there are significant differences between the shifts. But we do not know which shifts are different. For this, we would need to perform a post hoc test. There are a multitude of these that are beyond the scope of this discussion. Tukey-Kramer is one such test, not to be confused with Turkey-Kramer. Putting it all together, in summary, there are many statistical tests at our disposal when performing inferential statistical analysis. In times like these, a simple decision tree can be extraordinarily useful. So we borrowed this from the World Wide Web, taking us down our decision tree on what to use. Let's follow this along to the ANOVA examples. Predictor variable, categorical or quantitative. In our case, it's categorical because we're talking about the individual shifts, shifts 1, 2, 3, and 4. Outcome variable, categorical or quantitative. It's quantitative because we're talking about the production rate. And now it says, do a comparison of means test. How many groups are being compared? If we had 2, we could do a 2-sample t-test. But in our case, we had 4, right? Shifts 1, 2, 3, and 4. So we go down here. How many outcome variables? We had just 1, so we do an analysis of variance. You might be asking, where does Mood's median come into play? Mood's median, as we said above, is a particular version of the chi-squared test statistic. It is the chi-squared test statistic, except we have pseudo-created a categorical variable here by taking the quantitative variable, that is the rate, and creating a new group that describes whether the rate for any individual observation is above or below the grand median. And that's how we apprehended this question and moved it over to categorical. Right, so that is why Mood's median is a special case of the chi-squared test statistic. We made up a new category. The category was, is this observation above or below the grand median? So that's how this fits into the chart. I think we will leave that for here today. When we meet in person, we'll run through an example now of actually running both Mood's median and analysis of variance on the truffle data set. But more or less, this is a repeat of what we saw above.